we call it, is this one. It's a circle with an omega in it. That's an ohm meter. In my case, it's still the same device, but we configure it as an ohm meter. Now, in principle, when you want to measure a resistor, in my case, it's the resistor R here in the circuit, you connect the ohm meter in parallel to this resistor. So you connect it to the two terminals of the resistor, just as the voltmeter. But you should not do it while the resistor is still connected to something else. So when you have this circuit with a voltage source supplying current to a resistor, and you want to measure this resistor, you have to take the resistor out of the circuit. Now, take it out and connect only the resistor to the ohm meter. Why is that important? We again look into the instrument. How does it work? There are several options how these things can be built. This is one that I'm showing here. Now let's assume that inside the instrument there's a current source. It's a constant current source. This current source supplies a current I to the external resistance R that we want to measure. Now, of course, when I flows through R, we will see the voltage across R. This is the voltage V. And this voltage is then connected to the ohm meter terminals, of course. And since our instrument internally can measure voltages, it is a voltmeter too, we can, at the same time while we supply the current, we can measure the voltage, the terminal voltage. And now there's the microcontroller, this little computer. This little computer knows the current I, because it has been defined internally when somebody built this instrument. It knows I. It now knows V because it measures V, and R is V divided by I. And this value, this calculated value, will then be displayed. Okay, so this is how it works. Now, imagine that you had not taken R out of the circuit, and the voltage source that was connected to R is still connected to R. Well, let's say the voltage that this voltage source creates is VQ or whatever. What happens now? What is the problem? Yeah. You're saying the direction of current will be the opposite? No, not really. The current, without the external voltage source, the current I will flow into this direction through R, right? When I now connect the external voltage in this way, with this voltage direction, there will still be a current flowing in this direction through R. Yeah, of course, we will also see a current flowing on that side, the voltage source, but the direction does not change. Like, we will see a current, technical current direction flowing in this direction here. Now, from the positive side of the voltage source through the load, basically, or through the circuit, to the negative side of the load, of the source. Now, I have still not given this arrow a name here. What kind of current is that? Is that still I, the current which comes from the internal current source of the ohm meter?
No, it would be I plus IQ.
with the I plus IQ. It's a different current. And basically, the voltage here, the voltage between these two terminals, is now determined by VQ, by the external voltage source. It's not a result of the internal current I and the external resistance R anymore. But the ohm meter simply measures this voltage. And it knows only the internal current I. So what happens? The ohm meter will take this voltage and this current and calculate some resistance value and then display it. And you may believe this value, but this value just makes no sense at all. Now, it's the wrong voltage which is taken for the calculation. So this does not work. When you use an ohm meter, you always have to take the resistance out of the circuit. Nothing else should be connected to the resistance anymore. You can, of course, measure, let's say, a resistive network if you want to know the total resistance of that network. You may have 2, 3, or 10 resistors connected to each other in some way, in series, in parallel, whatever. If you want to know the total resistance of that circuit, you can, of course, take that circuit, but make sure that there's nothing else connected to that anymore. Okay, taking the resistance out of a circuit may be difficult in some cases. If you have a complicated system on a PCB, on a printed circuit board, it can be hard to really detach the resistance and then measure it and then attach it again later on. So sometimes it's just not possible to use an ohm meter for measuring resistances. In those cases, you can try to use a voltmeter and an ammeter and do these two measurements yourself at the same time. The voltage measurement is usually not the problem. You can always just connect or use your probes and just connect them to the two terminals of a resistor on the PCB while the current is flowing. The issue is always with the current measurement, because you have to connect the ammeter in series. Now you would have to, I don't know, scratch the wire on the PCB, for instance, and then connect the ammeter in between, and then close the gap later on again, so that the system is okay again. If it's not really a product that you're looking at, it may be a prototype. You can also design your PCB in such a way that you can use an ammeter in certain positions. Just put some connectors there, not just the wire, some connectors. Then you can put a so-called jumper on these connectors in order to establish the connection. And if you want to measure the current, you just take off the jumper and connect the ammeter in between instead. So this is frequently done, basically, in prototypes, not in systems and product systems normally. Okay, so in general, you can of course try to do this, yeah, measuring voltages and currents at the same time. But there are a few things that you should take into account, and it has to do with what we said about voltmeters and ammeters before. Now let's look at this first option. There is a resistance, or a resistor R, and this is somewhere in the system. And we want to use an ammeter and a voltmeter in order to determine the resistance which is there. So we have the voltmeter connected in parallel to R, and we have the ammeter connected in series with R. Is there any issue with this circuit? We will get definitely two values, the current value and the voltage value. We can divide voltage by current, and we will end up with a resistance value. But is this really the value of R, or what is it? you see that I've drawn real voltmeters and real ammeters, right? Not ideal devices.
So we have to first make ideal.
Pardon?
First make it this ideal.
We can't do that. We will never have any ideal voltmeter or ideal ammeter. We always have real ones. And these devices have inner resistances, as we saw before. I have drawn this here, circuit. The voltmeter has a resistor, an inner resistant RIV in parallel or between the two terminals. So it's basically in parallel to the voltage that we want to measure. This is the ideal part. This is the real part here with the inner resistance. Now the voltage which is measured between these two nodes is really the voltage which appears across R. This is the voltage we want to measure. This is good. But what about the current that we measure here?
Well, it's going to be split between the voltmeter and resistance R.
Exactly. We have a current flowing through R. This is the one we want to know. But there's also a current flowing through the voltmeter, through this inner resistance. And our ammeter is measuring the sum of those two. This is Kirchhoff's current law. The current I is IR prime plus IR. So we are not measuring the right current. In German language, we call this spannungsrichtige Messung. If I translate this to English, it's voltage correct measurement. But I think in English language, this doesn't really exist. People don't use these terms really. I couldn't find anything like a good translation. So I just stick with the direct translation between German and English in this case. We call this the voltage correct resistance measurement. So is this worth anything if we know that we do, or that we make a mistake here anyways? Well, first of all, it depends on the ratio between our resistor R, the one we're looking for, and the inner resistance of the voltmeter. We said before already, this inner resistance should be very large. If this inner resistance is much, much larger compared to R, then maybe the mistake we make is just negligible, because the current, the portion of the total current that flows here is very small compared to the one here. So we can basically determine failures with a good accuracy with this measurement. But this is not the entire story. Because the mistake we are making, even if the inner resistance would be in the same range as R, the mistake would be large at first. But it's a systematic error. Because we know the inner resistance of the instrument. And of course, we know the voltage. We're measuring the voltage. So we can calculate this part of the, or this portion of the current. And if we can calculate that, we can, at the end of the day, just subtract it from the measured current. So we take the mistake away, we eliminate. And this is what we have written down here. When we just take the measured values, the measured voltage and the current IR, which we cannot really directly measure, we can replace this current with the measured current I and subtract IR prime, the current through the voltmeter, and the current through the voltmeter is just the measured voltage divided by the inner resistance. So you can apply this formula and eliminate the mistake, the error. And then it's fine. The measurement is good. It's a systematic error. You can compensate that or correct it. Now, there's an alternative too. If you already know that the resistance that you're looking for is probably very large, then you know this circuit is not very good because you get a large error first before you correct it. So you could modify the measurement slightly. You take this wire and connect it there. So this is shown on the next slide. The only thing I've changed is this connection here. It's not connected to the resistor directly. I now measure the voltage across R and the ammeter in series with R. I measure the total voltage. The ammeter is now measuring the correct current. It is really the current which is flowing through R. So I is equal to IR. But V, the measured voltage, is not equal to V, the voltage across R anymore. And there's a problem with my slide. I just noticed that now. This should not be called V. It has to have a different name. It is basically, what is it? It is VE. It's the same as the voltage at the input of the circuit. So it's a different voltage. It's not the voltage we're looking for. Is it a problem? Well, if our resistor R is very large and we connect a very small inner resistance of the ammeter, then maybe the mistake is just negligible again. So this configuration is good for determining large resistors. You may not need to compensate this error. If you have to, you can also do it with this type of circuit. It's even more simple than before, because when you take the measured voltage and the measured current and divide voltage by current, what is the result? The result is the series connection of R and RIA. You know RIA, the inner resistance of the ammeter is known. And then you just subtract RIA from the calculated resistance value. That's what you see up here. I take the measured values, V and I, divide V by I, and then subtract the inner resistance, and that's it. It's a systematic error again. We can correct it. Okay, I call this the current correct configuration, and it's again just a direct translation from German to English, so it's Dinglish. You may not find these words or these terms in the books. Okay, so whenever we use the one or the other configuration for this type of measurement, we make a mistake. It's either the ammeter that introduces the problem or the voltmeter. Why can't we just eliminate the issue by first measuring the current and then taking the ammeter away and then measuring the voltage with a voltmeter only? Why is that not a good idea? I mean, in principle, when you take the voltmeter out of the circuit here, you will definitely measure the current that is flowing through the resistor R. If you take the ammeter out and leave the voltmeter in, you definitely measure the voltage across R. Why is it a problem? Yeah.
Because when you add a meter or voltmeter, you always slightly change in the circuit, and so you would in theory get two values for two different circuits. They don't really